Yeah, let's make a start. So yeah, thank you all for coming. Yesterday I gave you the big picture overview of what's going on with this mini course, and I said that there was a main theorem, a hook, and the main theorem was basically the combination of these two theorems. Okay, theorem A prime and theorem B. But something has happened. I'm going to have to explain what's going on here. Yeah, so I gave you a big picture overview yesterday. I was watching the video of the talk late last night, and I had two realizations. One is that I guess I'm somewhat of a narcissist. This was not a pleasant realization. But the other realization was that I gave this whole talk, and I didn't write the word definition on the board once, which may or may not be a record for the IHES. I plan to rectify that today. So today you will almost exclusively see definitions. You have to appreciate that I'm somewhat of a probabilist, somewhat of a ergodic theorist. So I'm used to things working out on average. It's okay if they're not completely correct every time. Right, so what happened to these theorems? I received some advice when I was in Budapest recently by my old boss, Marcin Szabok. He sat me aside and he said very emphatically, Sam, once you are done preparing your IHES lectures, you need to scrap everything and then start it again, but make it 50% simpler. One thing he omitted was how many times I should iterate this procedure. And so appropriately enough, I sampled from a Poisson random variable, and I iterated it that many times. If you like, you can try and guess the mean of this random variable. I think 3, but yeah, so I've decided to simplify things to just focus on the countable setting. Okay, I do this for a bunch of different reasons, but the simplest is just that this is more of an audience of, I don't know, geometry people or dynamics people or something. And so I think the probability theory might be a bit overwhelming, whereas everything will be much more elementary, as you'll see soon. And so theorem A prime now, it's the vanishing of rank gradient for Faber sequences, which I'll define tomorrow, but now just in the setting of a finitely generated group. Okay? And I've put these other names on it because that's not my theorem. So it was proved by two independent teams. One is Mikolaj Fraczyk and his former PhD student Laszlo Tóth. And then independently by different methods by Kaderi, De La Salle, and Gilborio. So the first team, they used what's called combinatorial cost and local global convergence, whereas the second team used groupoids and ultraproducts. And I'll prove this theorem tomorrow. Okay, you'll see that it's a very slick proof. And if I'm honest, I mean, it's not my proof. I do have a contribution to it. I'll make it very explicit what my actual contribution was. But this proof, I would say, essentially goes back to Abert. And it's different from these other two proofs. Okay, so you'll see it's very nice. And the key tool in proving this statement, as well as proving this theorem B, is a statement called cost monotonicity, which is some kind of semi-continuity of the cost function on the space of actions with respect to weak convergence. So this is something I'll explain tomorrow. And there is a basic fact that I think I mentioned yesterday, I'm not sure, but it's related to this suspension construction that Homin was talking about. And it says that if you take a lattice, then it turns out that the cost of any lattice action is related to the cost of what's called its induced action. And it's related by this formula. Okay, so there's all these -1s appearing. You'll see why. And I plan on more or less proving this, or at least the relevant inequality, by the end of the talk, assuming I have time. And theorem B, this one stays the same. Okay, so this is just saying in higher rank you have fixed price 1. The cost of the Poisson point process is equal to 1. For the purposes of this talk, you can take that as a definition. And now, finally, I have to actually define things. So I will start with cost. Okay, the setting here is that we're interested in gamma being some countable group. So no longer can we think SL3R, so I guess we have to think SL3Z. That one's pretty good as well. And I introduce some notation. I'll write blackboard M for, just as a little shorthand, for the space of subsets of this group. And I will adopt some terminology from percolation theory. I'll call this the configuration space. So this is the configuration space of subsets. omega inside gamma. Okay, this is terminology I get from percolation theory. I think it comes from statistical mechanics or something originally. And now we start to see the advantages of me switching to the countable setting, because now, I mean, this is some nice space that you're all familiar with. This is just the Cantor set. And I equip it with the usual topology. Okay. And now I have a bunch of definitions and examples to work through. So the first of these is a point process, right? So pi is an invariant random subset. Exactly what it sounds like. Invariant random subset of gamma. So if I were cheeky, I would call this an IRS, just to annoy Mikolaj. But instead, I'll call it a point process. Okay, and what does invariance mean here? Oh, one more bit of notation. I write mu for the law, or distribution of pi. Okay, this is the associated probability measure on this space. So if you prefer, you can think about things just in terms of this distribution. But I will continue to write things as random subsets, because that's the point of view I'm trying to get you all familiar with. And so, yeah, what does invariance mean here? Invariance. In the probabilistic notation, what it means is that gamma pi, so a priori that is some other invariant random subset. Invariance means distributional invariance. So the distribution of this invariant random subset is just equal to pi. Okay, so pi is statistically homogeneous. And if you prefer to think about things in terms of the probability measure, equivalently, this means that the action of gamma on the space of subsets equipped with the distribution, that this is PMP. Okay, probability measure preserving. Okay, so now let me give you the two examples that we will need. So, examples. So the first of these is perhaps the simplest. This is Bernoulli random, so Bernoulli. And I will denote its measure by Ber-P. And this is just you flip a p-biased coin independently for each element. Independently for each gamma and gamma. Oh, whoop. Gamma and gamma. And then you let pi be the set of gamma that received head. Okay, so gamma got head. Head. Sounds weird otherwise. And here, what is the measure? The measure associated to this is mu is just this combination of Dirac masses. Okay, so it's just just the product measure. Okay, this thing that I wrote here and this thing, they have the same mathematical meaning. Okay, and it's up to you as to which one you prefer. The next one, this is the only other example we'll need, is the lattice shift.
Wait, did P become a half of point?
Yep. Yeah. Sorry. Yeah. Okay. So yeah, what we need is the lattice shift. And so here, lattices are just finite index subgroups, right? So where lambda inside of gamma has finite index. Okay, and what is the associated point process in this setting? you just pick a coset A lambda at random, uniformly at random. Okay, and I'll write down the measure begrudgingly. So it's 1 over the index, and then it's a sum of Dirac masses. So A lambda in gamma mod lambda, and then the Dirac mass at A lambda. Okay, once again, these two expressions have the same formal meaning, but one of these is better than the other. Okay, more definitions. This one is also important. Definition. So the intensity of pi is, what's that? It's int pi. And this is, by definition, just the probability that 0 is in pi. And here, 0 in gamma is the neutral element, the root, the identity, any fixed point, root, identity, base point, whichever term you want. Okay, some people find it disturbing that I use the letter 0 for this, despite the fact that this is not an abelian group, but that's the convention in probability theory. Okay, so I'll just state some basic properties of this intensity. So for our examples, the intensity of the Bernoulli P measure, this is P. And the intensity of the other guy, of the lattice shift, you can check, this is 1 over the index. Okay, this is an elementary calculation. It's an elementary calculation using invariance. Okay? And one useful thing to note, which I think I'll use tomorrow, is that the intensity of pi equals 1 if and only if, well, pi is just the whole group, almost surely. And similarly, the intensity of pi is 0 if and only if pi is empty, almost surely. Okay, these are statements that should be obvious for you. So if they're not obvious, then I recommend that you attend the exercise sessions. Questions about invariant random subsets?
Is the intensity P or 1 over P?
P will be between 0 and 1. So, yeah, sorry, I should have said this. For probabilist P is between 0 and 1. Yeah. Okay, so that's invariant random subsets. These are the only characters we'll really need to prove this theorem, surprise, surprise. We will need a more general notion, and that is the notion of invariant random colorings. Okay, so, definition. Are you getting sick of this yet? Definition, an invariant random an invariant random 0, 1 coloring of gamma is a random element, pi of this space, 0, 1 to the gamma. Okay, so I'm thinking about the unit interval as representing a spectrum of colors, I guess. And yeah, this is the notation I'm going to use moving forward. If you prefer, you can think about it as a Borel probability measure on this set, which is P and P. Okay. And here is almost the only example we'll need. I'll have one more example tomorrow, and that's where the Faber condition will come into play. And this I will denote Bernoulli 0, 1 with square brackets. And this is just IID uniform labels. So in other words, this is the Lebesgue measure on the interval, the infinite power. Okay. So I say this is the only example that we'll need, but there's something that I want to point out, especially to the young people who may not know this. Here is a remark. Okay, every PMP action, gamma acting on some mysterious space, x mu, a probability space, is isomorphic to some invariant random coloring. Okay, and I won't prove this. This is in the exercises. It's a very simple exercise. You may know this as looking at the associated symbolic dynamics of the action. But there is a slogan here, which is that they are the only game in town. Okay, so depending on your sort of exposure to ergodic theory and dynamics, you might be looking at these symbols here, gamma acting on x mu. Wow, there's so many spaces. There's manifolds, and wow, there's really just manifolds. But there's lots of spaces. There must be so many ways of making it act. And what I'm saying is that whenever you say PMP action, I'm automatically thinking invariant random coloring. Okay, up to isomorphism, there's no loss of generality. You might think that these invariant random colorings are somehow silly actions that only probabilists care about. But the lesson here is that up to isomorphism, that's all there is. So if you're serious about these things, you have to engage with these things. Yeah, and there is an advantage here, and this is what you'll see tomorrow. Okay, if you just think about this space of PMP actions, now that I'm modeling them all in one fixed space, the space is fixed, the action is fixed, it's only the measure which is variant, I get access to a very powerful tool. Okay, so I only have like 2 or 3 tricks, and one of them, my trusty little 6-shooter, is something called weak convergence. And weak convergence can magically solve problems for you. Okay, that's what happens with this tessellation. That's also what happens with my recent paper on constructing cost-1 actions for Kazhdan groups. Yeah, so okay, these are the actions that I'm going to consider, and I wanted to describe what cost was. So this was point processes, more generally these invariant random colorings, and now we want to connect them up. We want to put some kind of graph structure on this set of points. Okay, so you remember I drew this picture, the potato, scattering of points, and I wanted to think about graphs on it. Okay, so now I'm going to give you a proper definition of that. So here we go again, definition. So I will denote this by graph gamma. Probabilists would call me perverse for even putting a name to this, but anyway. VE, what is a graph, right? A graph is a collection of vertices and edges. Except I want my vertex to be a configuration. And then I want the set of edges to also be a configuration, but it should be on gamma times gamma. And what I want is that E defines a graph structure on V. Okay? So that's just saying that E is contained in V times V. So if you wanted to be a bit pedantic about this, this is the space of directed graphs. Graphs on, well, configurations in gamma. Okay, directed graphs, no loops, no multiple edges, or whatever, but once you see a definition like this, you can write down any kind of graph that you want. Okay, the only limit is your imagination. And so I was using this terminology of factor graph yesterday. A factor graph was one of these rules for putting a graph structure on the point process. So now I can actually say that more formally. So a factor graph The underlining means that I'm defining something. A factor graph of pi is now some invariant point process, is a measurable map. I'll use script G, going from the configuration space to the space of graphs, satisfying two simple conditions, which I guess I have to move to another board. Oop. So satisfying two conditions. So what I want is that the factor graph is a graph on pi specifically. Okay, so such that for all gamma and gamma, if I look at the graph on, well, gamma times pi, that's equal to gamma times the graph on pi. Okay, there is a natural action on this space of graphs. You're just acting diagonally by the shift action. So this condition, this is equivariance. And the other condition is that, and the vertex set of G of pi is pi. Okay, and because of this redundancy in my encoding, like the vertex set is always going to be pi, more or less, I will just specify the set of edges when I'm specifying one of these factor graphs. Okay, one more bit of terminology, and then I'll show some examples, which will hopefully be clarifying. So if G of pi is connected pi almost surely, then we call this factor graph G a graphing of pi. Okay, so I believe there are a couple people who have heard of Campbell-Borel equivalence relations, so this terminology might be familiar, but you can just take it as a definition. It just means something that's connected almost surely. Okay, and now I can give you some examples. So example. So if D is a left invariant metric on gamma, okay, I think these things pretty much always exist, right? Then I can define a factor graph as follows. So R here is some parameter greater than 0. I could define dr of omega, so it's a Borel fella. This is just all pairs of points in omega such that the distance between them is less than r. Okay, this is the distance r factor graph. And let me just point out that this is typically not connected. Okay, for instance, if you think about this Bernoulli process, you should be able to convince yourself that it's never connected. Okay, it might have a unique infinite connected component, and that could be good enough, depending on what you're looking at. Okay, so the study of this particular factor graph for something like the Bernoulli process, that is something in the realm of percolation theory. Okay, so that's like a subject of mathematics in its own right. There's a fella over in that building who's got one of those shiny Fields medals, and I think a big part of what he does is pretty much just looking at this graph. So, you know, simple definition, but things can be hard. Are there questions at this point about this factor graph notion. The main thing I want to emphasize, typically when I explain this, people get a bit confused. This is an example of a factor graph. There are many, many of these factor graphs. Okay? The examples that I give will have a similar flavor, but in the third one, you'll automatically see that this is not like the ones that we usually work with. Okay. So here is another example of a similar flavor. So if, sorry, I'm in the shadows. If S inside of gamma is finite, we're in France, so I can use this notation. If this is finite and symmetric, I don't know if I really need this, but just put it in there to be safe. Finite and symmetric, then I can define a factor graph called the Cayley factor graph. So K omega S. This is just all the pairs X, X, XS, pairs in omega, such that S is in S. Okay, this is the Cayley factor graph. And something you should check is that, well, I mean, this is a graph defined for any configuration of gamma. So I could put in just gamma itself. And you could ask, well, when is this connected? And I'm sure you can all figure this out. This is true if and only if S generates. Okay. More generally, or slightly relatedly, more generally, if I put in some finite index subgroup, for instance, so if lambda inside gamma is finite index, the finite index doesn't really matter, then the Cayley graph on the lattice shift, so now I pick a random coset, you can ask, when is this connected? This is connected. So it is a graphing if and only if S generates lambda. Okay. So one final example. If gamma is infinite and amenable, and this is a property I believe that you guys know, then any let's say non-empty invariant point process pi admits Z as a graphing. Okay, and this, you know, once you process the definitions, this essentially goes back to Dye, Ornstein-Weiss, and maybe even Kohn-Feldman-Weiss. I don't know exactly. Is it one N or two N's?
What?
Feldman.
That's fine.
Okay. Okay, so this is an important example that I may talk about tomorrow at the very end, if there's enough time. But I mean, as you can see, however this graph is defined, it's very different to, for instance, the distance R factor graph. Okay. So that's factor graphs. And there's one more kind of example I want to introduce. And this is how we make the connection to what some of you have been calling classical cost. So here is an example. So if G is a graphing of pi, and pi here should be non-empty, right? Then G can be extended to some other graphing, G tilde, which is bigger than G, such that the vertex set of this G tilde is gamma, and the points of gamma minus this random subset pi all have degree 1. Okay, in graph theory terminology, you would say that they are leaves. Okay, and there's another important condition, which I guess will be another one of the exercises. Also, this G tilde is locally finite. This is important for cost reasons. Okay, so in other words, it has finite degree. And the picture here, I think, should make it clear. So what's going on here? This is my group gamma, and inside of it, I have this random subset pi, which typically is not the entire thing. I mean, we're trying to extend this graph to the entire thing. So I have G of pi is some graph on the set of points of pi. And all I'm doing is I'm taking every point outside and just connecting it to, say, the closest point that happens to be here. Okay? Just like this. And so if you do this correctly, you will get something that's still locally finite. Okay. So now, with that all out of the way, I can finally define cost. Okay, so I guess I'll do it here. So here's the definition. So cost is defined for invariant point processes, also invariant random colorings with the same definition. So I'll just state it for point processes. And the formula will look a little strange at first. So the cost of pi minus 1 is equal to the infimum over all graphings G of 1/2 of the average degree of G, such that G is a graphing. And then there is a normalization constant that you need to add in here, which is the intensity of pi. Okay, so if you're familiar with classical cost, all I'm doing is making the translation of cost for this specific kind of action in terms of this complete section, the set of rooted subsets. Okay, but I'll try to avoid explaining this too much in the lecture. I can talk about it in the exercise sessions. But that's why we end up with this -1 and this intensity going on here. Okay, and so by induction, something called induction, so this goes back to Damian, as pretty much everything does. By induction, or what probabilists would call mass transport, so I'll say a few words about mass transport, the cost of pi can be expressed in maybe a slightly more simple way as, again, the infimum over all graphings of 1/2 the average degree. But now I take it for this special extension that I constructed above. Okay, and what is the advantage of this extension? Now I don't need to worry. I made the same mistake on the board and in the notes. G is a graphing. A graphing of pi. okay, where this G tilde is as above.
Okay. And you're not subtracting the canceling? Yes.
No. So the mass transport, it tells me that, I mean, if I'm thinking about the fraction of the space that is a leaf in that picture, the points outside of pi which are leaves, they have measure 1 minus the intensity of pi. Yeah. And so, yeah, if you sit down and you think about something called mass transport, which I'll explain momentarily, you see that those things cancel out. So that's the advantage of this formula. And I should say that, you know, I didn't invent this perspective. If you look in the book of topics, I didn't know about this until very recently, but if you look in the book Topics in Orbit Equivalence by Kekris Miller, they have a chapter, Kekris Miller, they have a chapter on cost and invariant random spanning graphs, and they explain this perspective. I learned this from Mikolaj. Okay, so there is an obvious objection here. What is average degree? So yeah, I'll get rid of the theorems. So what is the average degree? What I want you to do is to fix your favorite finite subset. Non-empty. No cheating. And then you define the average degree of some general factor graph. It doesn't actually have to be a graphing. It doesn't have to be connected for you to make this definition. To be, not that. To be an expectation. So I want you to sum over all of the points in your finite window and pi. And then you take the degree of that point computed in this graph G of pi. And then we're supposed to be averaging, so you should divide by, sorry, I'm used to locally compact groups, so it should be Haar measure, but that's just the size of the group, size of this subset. And what you should check, this follows from the existence and uniqueness of Haar measure. But in the Campbell setting, everything's nicer. So this does not depend on the choice of U. And so, you know, to make things easier for yourself in the exercises and so on, I highly encourage you to pick U to be just containing the identity. Okay, so this is the notion of average degree. There will be a bunch of exercises on it. I'll need to add them, but yeah, this is what it is, and this is the full definition of cost. And there is some more comments that I want to make about this. So it seems like the PMP-ness doesn't really come in yet. So that's going to come in now. So if I take an orientation of this factor graph, so in other words, I split the set of edges into two disjoint sets, which I label with arrows. So these are the ones going in and out. This is any orientation. then, and we're going to be able to fit these expressions on the board, then the expectation of the indicator of 0 being in pi times, so now I'm specifying, I'm just taking U to be this set, because I want things to be simple. If I look at the degree at the root, except I take the out degree, and I take it for the out edges, this is equal to the expectation of the indicator that 0 is in pi times the degree at 0 of the in degree for the incoming edges. Okay? So this is the mass transport principle. And it follows from an elementary fact, which I'll write on the next board. But something that I want to point out is that if you're a little more advanced in your probability theory, you might think of a way of writing this in a slightly simpler fashion. If I replace, I mean, when I multiply by this indicator that 0 is in pi, that's basically the same thing as computing this expectation with respect to the conditional measure, where I condition for pi to contain the root. Okay? That's literally by definition. Okay? And what I want to say is that in the locally compact setting, all this business with cost is a bit unclear, right? But if you just talk about cost for point processes, then this formula does make sense, because there is a way of conditioning on a point process to contain one single point. This is something called the palm measure. And I deliberately wanted to avoid speaking about it, because it's something that people find scary, even though it's really quite elementary. But that's something I would be happy to talk about in the exercise sessions or some other time or whatever. Yeah, but this is all this is. And how would you prove this? You prove this using a very elementary fact. Oop. Almost done. Okay. This follows from an elementary fact. So I'll just write fact. If I take a function on gamma times gamma, non-negative function, and this is diagonally invariant. Okay, so you can probably guess what this means, but I'll write it down anyway. F of gamma x gamma y equals f of x y for all gamma x y in gamma. Then it turns out that informally the way we say it is that the total mass in is the same as the total mass out. So the sum over y in gamma of what the root sends out is equal to the sum of what the root gets in. Okay, so informally mass in equals mass out. Okay, this is, this is really a very elementary exercise, but I encourage you to look at the book of Lyons and Perez if you want to see a whole bunch of applications of this. Okay, so as far as I'm aware, there are essentially two flavors of application of this mass transport principle. There are the ones which are extremely obvious. They prove something which is intuitively true, but this gives you a rigorous proof of why it's actually true. And then there are the crazy ones that Tom Hutchcroft and Adam Timar cook up. Like they prove crazy things about percolation objects. Okay, so examples, right? Examples. The simplest process I can think of, pi is just gamma almost surely. What's the cost of that fella? Well, if you're keeping track at home, the cost of this is equal to d of gamma. We saw this guy yesterday. That was the rank, one of the few things I actually defined. Here's another example. Pi is a lambda random coset then the cost of the corresponding lattice shift action minus 1, that's this mysterious minus 1 over there, this is equal to the rank of the lattice, rank of the finite index subgroup, divided by the index. Okay. In general, the cost of some point process pi is at most the rank. Okay. So these were all of the examples we need. This is a formula I promised, right? And now, if you actually follow the definitions, you'll see why it's true. So there's one more definition that I want to give, and then I want to construct the Poisson point process very, very quickly. Which board would be the best to remove? Top one? That's the simplest, right? Okay. Oop. Okay, so here is a exercise / definition. Okay, I'll call it an exercise with the definition smuggled into it. If phi from the configuration space into itself is measurable plus equivariant, then if I apply this map to some point process, by definition, I get an invariant point process. Okay, pi here is an invariant point process. So the terminology that I was using yesterday without strictly defining is that we call pi, we call phi, or phi of pi, a factor of pi. Okay, because it's like a factor map in ergodic theory. And these factor maps, they come in all sorts of flavors, and you'll see a few of these. And one thing that you can check, this is the exercise component, is that cost is monotone for factors. Okay, this is very important. So cost of pi is less than or equal to the cost of phi of pi. And then I have a follow-up question. Can it be strict? Can this inequality be strict? And the hints, there's a hint on the exercise sheet for this one, which is that we don't know any group that doesn't have fixed price. So this statement is probably false, right? Okay, so that's all the definitions. And in the remaining couple minutes, I just want to say something about how you actually construct the Poisson point process. So if you haven't seen it, this is, I want to construct it as a factor of something, a factor of the Bernoulli shift on the group. Okay, so this will be important for tomorrow. So the setting here now is that I have G is some LCSC group. And now I define its configuration space, which is slightly different. But it's just all subsets such that G is locally finite. Okay, locally finite with respect to some nice metric on the group, so a proper left invariant metric. And then how do I construct the Poisson point process? This is something that I've been talking about in the exercise sessions. So I want you to take gamma inside G, a lattice. You guys like lattices, right? I'm going to draw this one, because that's the only one I know how to draw. Well, I guess I could do ASL2Z, but I don't want to flex on you. I want you to generate pi as follows. Okay? And this is just a bit of jargon. When I say generate, I am explicitly defining a probability measure for you. Okay? So think about the partition of your group into translates of the fundamental domain. And in each cell, right, these are all just finite volume things. I want you to put down Poisson many, a Poisson random variable many, with parameter what? 1 over the covolume. Many points independently and uniformly at random. Okay, that means with respect to the Haar measure, or rather the restriction of the Haar measure to those subsets. And so there are various things that you need to check, and I emphasize that mathematics is not a spectator sport. You don't understand this by watching me do it. You have to do it yourself. So I want you to check that this does not depend on the choice of gamma. Okay? Not only does it not depend on the choice of gamma, I mean, it doesn't really depend on the choice of this partition at all. If you did this sampling rule for an arbitrary partition into finite volume pieces, and you put down the appropriate parameter of Poisson many points, then you would end up with an invariant point process. Okay? One thing that I was supposed to say was, I mean, the naive approach of generating a nice invariant random subset of the space would be you just put down 1 point at random. Okay? 1 point at random in each cell independently. But it's very easy to check that this is not invariant, so it's not valid. So maybe you try putting down 2 points, 3 points, 4 points. Each one of these is equally futile as the last. The magic distribution that saves the day is this Poisson distribution. Okay, there are very elementary properties of the Poisson distribution which show that this is actually giving you something invariant. Okay, so the resulting subset is invariant. Okay, this is a very elementary exercise involving binomial coefficients. Here's another fact. The intensity of this fella is 1. Right? That's why I put 1 over covolume many there. And an explicit exercise is construct this, so construct pi as a factor in this sense, of the Bernoulli shift of gamma. So 0, 1 to the gamma, Lebesgue to the gamma. Okay, I had basically done it for you, right? These cells, they're indexed by gamma. And if I have a 0, 1 random bit, I can use that to simulate any process at all. Okay? And so I basically did this in the exercise session today, or one of the exercise sessions, I don't know, I lose track of time. This is some product. I mean, you could define some explicit map from some huge product that looks like this. So all of these shifted tiles, F here is a fundamental domain for the lattice, and then you're constructing some explicit map phi to the configuration space of G. Okay, you can write this down explicitly, and now you really see, I mean, this is what I mean by a random element of this space. This is some probability space. And what you're supposed to take away from this is that this is a useless representation. It tells you nothing about how to prove anything about the Poisson. There are some more exercises that I will just list very quickly, because I only have, -2 minutes. Okay, exercises. Here's the first one. Poisson action is free. Free, if and only if. Free is in essentially free, if and only if G is non-compact. So this one we did in the exercise session today. Poisson action is ergodic, in fact mixing, with the same proof as in the countable setting for the Bernoulli shift, if and only if G is non-compact. And then the final one this is maybe the challenge exercise where you can teach me something. There is something I don't understand. I have a vague idea of what it is, but it's called Wiener chaos. This implies that the Poisson action has spectral gap if and only if the ambient group G is non-immutable. Okay, I know a little bit about spectral gap, and I know that it's some sort of powerful tool, but the challenge is apply this. I don't actually know of an application of this, so I'd be very interested if you can tell me one. Okay, and that's all.
Do you know of any other invariant point process, say in the unit disk, hyperbolic unit disk, or something where cost has been calculated?
I mean, fixed price is known for SL2R. Yeah, I don't know any slick argument other than that one, which is not a slick argument. It's a hard argument, but yeah.
So your construction only works for unimodular.
This construction? Why?
Because there exists a lattice if and only if G is unimodular.
Yeah, but I didn't need the lattice, right? I mean, this construction works in general. You just need to take some partition into equal volume pieces. So yeah, in a very pedantic sense, it required it to be unimodular, but yeah.
They don't need to be equal volume.
Yeah, they also don't even need to be equal volume. I mean, they exist, yeah.
Yeah. Second in your checklist, the result is G invariant?
Yeah. G invariance, like it's a G invariant point process. Yeah. Yep.
Has someone studied these four Polish groups, like the PNP actions?
Yes. There are 2 recent papers on this. The authors I cannot remember off the top of my head, but I can show you those, yeah.
Any last questions? It's next time again.